Sorry, on. It's a great pleasure to have today's speaker, Amy Novick-Cohen from the Technion Israel. We speak about very interesting research. We're going to take Amy out for restaurant right after the talk. Please let me know if you can join us.
These lights sort of glare.
Yeah.
You know which is the...
I'll find you in a second.
Yeah, better. Yeah, good.
Thank you, Dr. Z. Maybe the PDF one?
Yeah.
Hey.
Hi, I was, yeah.
How you doing?
Okay. I'll try to... I talked to Eric who told me about movies of yours that I'd never...
Okay, you'll be gone. You'll be gone.
Okay.
The talk is already started.
Okay, clicker.
Okay. You don't have a clicker? Okay, it's okay. I'll click here. Okay. So I thank you for that kind invitation, and I'm happy to come back to Rutgers and in fact to speak for the second time in the experimental mathematics framework. Okay? So what I'd like to talk about today is coarsening and the deep quench obstacle problem. The first half will be general theoretical results, and the second half, which I'll make an effort to get to in appropriate timing, is numerical results, which is a verification of the theory and also a possibility of raising additional questions of potential analytical interest, okay? So that can be labeled experimental mathematics, okay? Numerical.
So you're allowed to speak here?
Yeah, so hopefully I'm allowed to speak here, and if not, I hope for negative feedback. Okay, but I'll do my best to be within the framework. Okay, I think it's okay. Okay, so here we have it.
Space.
How do you go forward?
Yeah, I can hit the space bar.
Oh, okay, I don't know. Okay. And what do I do to go back? P? P.
Or oops.
Oh,
Oh, sorry. Right left is okay.
okay. So part of this I think some of you have heard before, so I'll try and go through that in some... in order to get to the deep quench obstacle problem, I'll get to that via consideration of the Cahn-Hilliard equation, which I've been working on for many, many years. And in addition, in considering the deep quench obstacle problem, we'll also have some considerations of a model from Ono and Puri, okay, who came to the model independently. I'm looking at the Cahn-Hilliard framework because it's also a natural framework in which to look at the phenomena of coarsening, okay? And because the theory is rather involved in the Cahn-Hilliard framework, we'll get results valid in the Cahn-Hilliard framework, and then we'll focus in on a particular limit of the Cahn-Hilliard framework where the theory becomes simpler and perhaps conjectures become easier to attain. So here's the Cahn-Hilliard equation. I think you've seen it before. Okay, it's a fourth order equation. And f, little f, is a derivative of big F, which is a double well potential. It was derived by Cahn-Hilliard in 1958. Many people could say it's not a great model. but in fact it's also a model for lots and lots of other things, so one can look at it at this point as a generic equation. And then one wants to know, one isn't so interested in this in the framework of phase separation. At the moment, one wants to look at the benchmarks of the dynamics. And the general benchmarks of the dynamics is an initial phase, where if you take a perturbation of a uniform state and you perturb it, and with a small perturbation, if the initial state was unstable, then there's an initial period of linear growth. This is known as a linear regime. Okay? And then this is dominated by the most unstable mode. And then what happens in the system is there's local saturation to the bottom of the wells. Okay? And then afterwards you get different regions dominated by one phase or the other. The saturations grow as others shrink, and then the dominant length of the system, the dominant scale, increases, and this is the process known as coarsening. Okay? And just to look at some pictures for people who aren't familiar with this, these are pictures by David Iyer. They're now part of Trevethan and Company's Coffee Table Book of PDs, which is available on his website in Oxford. Okay? So you look at this and you can see that as a function of time, the length scale is growing. Okay? Anyone who knows this, it's trivial. Anyone who doesn't know, this is what coarsening means. Okay? And then we want to focus on some particular constitutive assumptions. So we take this to have this form of F. The first part is the ideal entropy of mixing, and the second part, the polynomial term, is the interaction energies. In terms of the mobilities, one can consider a degenerate mobility or a constant mobility. Okay? And because U is the difference of the concentrations of two components, it should lie strictly between -1 and 1. That's this constraint here. And the formulation as prescribed here goes back to Cahn-Hilliard over 15 years ago. Emphasis on the degenerate mobility case was undertaken by Eladin Garke in 1996-97. One has this full range of temperatures, but then, in fact, what happens is the temperature has to be sufficiently low, in fact, for there to be two wells in the potential. Otherwise, the two wells coalesce and there's only one well. So for theta below some critical value, there are now two wells, and theta, going back to this is actually the temperature, look at it as a Kelvin temperature, it really has to be positive. Okay? So we're interested in theta within some range 0 to the critical temperature, and then following an approach of Cohen and Otto and really Cahn and Hilliard, one looks at of interest is to focus on what happens to the shallow quench, meaning you take the temperature just a little bit below the critical value, and similarly one can take the temperature down to 0. Okay? In the first limit, the shallow quench limit, you also have to look at concentrations very close to the initial concentration. And you have to look at long length scales, long time scales. The deep quench limit, you simply take the original length scales and time scales and you take the temperature down to 0. In the first limit, you get what's known as the constant mobility polynomial Cahn-Hilliard equation, which was treated for many years. And the other limit you get, you would say, if you look at that, that's really an obstacle problem, okay? Because it really only makes sense for U between plus minus 1, okay? So it's written as a PDE, but it really has the constraint that U has to take on values only between plus minus 1. It's written that just for ease of presentation, and that similarity of structure. For this Cahn-Hilliard equation with the degenerate mobility, it's possible to write out existence regularity theory. The existence regularity theory written out here goes back to Elliott and Garke in about 1996, 97, but in a paper of 2002 by Cohn and Otto, they really are responsible for the bottom line, which says that it's nearly a Lyapunov function. It's something, the energy is something a bit weaker than an actual Lyapunov function. Okay? And here, okay, what can you say about coarsening? So the first people who approached this question of coarsening and the Cahn-Hilliard equation, meaning this degenerate Cahn-Hilliard equation and looking at these two different limits, the shallow quench and the deep quench, were in this paper by Cohn and Otto. They obtained rigorous upper bounds for the coarsening rates. Some t to the 1/3, t to the 1/4, t to the 1/3 being the rate they got in the shallow quench, t to the 1/4 being the rate they got for the deep quench. We looked at this and I said, because I've spoken with John Cahn over the years and worked with him, you really don't want temperatures either at 0 or 1. In terms of the physics, you want to know what happens for the full spectrum of temperatures, because that's what you really see in the laboratory. And also in their paper, there were certain restrictions. They said the mean concentration had to be 50-50%, half one material, half another. Quite obviously, you should like to have any arbitrary mean concentration, any mixture of two components, a small amount of a minor component, anything between 0 and 100%. So you want to take care of all of that. They also got bounds. Their bounds are good only at long times. You don't exactly want to know only what happens at long times. If you're looking at the laboratory, you really want bounds which are good for all times, or at least you want to know when, at what time you can start to trust these bounds. Otherwise, you can't actually prescribe what's happening. Okay, you don't know. You want to go into the laboratory, mix the chemicals, and tell people what they're going to see so they know when to put it in the oven and when to take out of the oven. Otherwise, you have to look at every moment and you can't, right? You're making some sponge. You want the sponge to have certain size holes in the sponge, okay? You have to know what has to be prescribed without, and that should be prescribed by theory, hopefully, right? And also for ease of treatment, they treated periodic domains. We treat arbitrary convex domains. Okay, but then we get out these prescription of what can be said in terms of rigorous upper bounds, but they're rather difficult to treat. It's still, you get these bounds, what can you actually go to say to someone who's in the laboratory? It's difficult a bit. So we look at this easier context of the deep quench obstacle problem with constant and degenerate mobility, okay? That in part is in this work in Journal of Statistical Physics, which I thank Joey is published in the Journal of Statistical Physics then, okay? And then in fact, even though we get these more delicate description, it's still difficult to know exactly what's going on. So we headed in and there's a lot of numerical work in order to try and see, you have these upper bounds, okay, but you still don't know what's the best upper bound, what's the lowest upper bound possible. So we did numerics much in the sense of what Constitutive was doing, okay, but with additional benchmarks, which allow things to be correlated in a bit of a different sense. It's also an easier framework in some sense, this deep quench, okay. Hopefully the different models and results can be correlated and can lead to some analytical theory. If not, tomorrow then soon. Okay. So here are the two problems treated by Cohn and Otto. The equation 4, that's your shallow quench limit, and one below isn't deep quench, right? It's where I said in words, just simply written out. Okay, and I've written out these two bounds that you get from the dominant line scale. That's just what I said written out here. And how do you go about getting upper bounds? This is the approach adopted by Cohn and Otto in this paper in nonlinearity in 2002. They defined two length scales. One is 1 over E, where E is the scaled free energy of the system, which was described before as acting as a Lyapunov function or something similar there too. There's L, which they took as an additional length scale. They couldn't quite work with just the one or just the other. And L is a pre-dual W1 infinity norm of U. Okay, more recently people have used a bit similar approaches but with slightly different norms. We adopted the framework of Cahn-Hilliard to see what that would give.
And that looks like a lower bound. It's upper bound? Because it's big or equal to. Superficially, it looks like a lower bound.
This is a lower bound, you're right.
Oh,
100%
you
right.
use it for an upper bound.
But if you read, you're looking at 6. Right. Okay, and in fact, Eric kind of got angry at me a bit confused, or I confused him. If you look up above it, 1 and 2, L is a length scale, okay? And at 1, okay, we're looking at the length scale e to the minus 1, okay? So if you look at what you have an integral there, that's an integral over, okay?
Oh, see,
1 over a length scale, okay? So in fact, what you want to use, you look at what's on the left, that's essentially okay, that's an LR 0T of this quantity E phi L to the minus 1 minus phi, okay? You take this LR norm, okay, and you invert it, and that's your length scale, okay? So when you invert that, okay, then you get this upper bound for that, which is 1 over C alpha T to the R over 3. Or in fact, then you have to, okay, you have to take the rth root, and then you get the 1 over 3, except it's good you also ask, because now I notice okay, that should be 3 plus alpha, please. Right, okay. That should be 3 plus alpha with, instead of T to the minus R over 3, should be 3 plus alpha, where alpha is equal to 0 for the constant mobility case, and equal to 1 in the degenerate mobility case. Okay? And since they undertook this in 2002, it's been used in many, many contexts. Their analysis is based on 3 lemmas. What we go about and do, it's joint work with Andrei Shishkov, which appeared in Discrete Continuous Dynamical Systems A in 2009, is we simply generalize their 3 lemmas, okay? Getting these more complicated forms. So it's previously the Cohn-Otto type, you wouldn't have this additional term. You just have A is greater than or equal to something, and in A you wouldn't have this term here with this boundary effect, okay? That's what they would basically have, and they'd ignore these other extra terms, okay? Those, but we get those taken into account here. And then the second lemma, in the Cohn-Otto context, you wouldn't have the second term on the right-hand side. That comes in by treating this full spectrum of concentrations and temperatures. And they also would have the U plus minus equal to 0, so they also would have the first term, the coefficient would simply be 1. Okay? And then the question is, what can you do with the first and second lemma? You can put them together and say that you have some sort of differential inequality as appears in the first line of lemma 3. And you can ask yourself, what can one do with such a differential inequality? So out of that differential inequality, it's possible to obtain in the sense of for an auto, 1, a bound from below on this quantity, which it gives a bound from above on the length scale, okay? And what comes out is written there. Okay, that's a generalization of omega. But in fact, what we can do, we can add in another effect, okay? If you know from before, either LE is greater than or equal to V, or you don't, sometimes if you don't know something of that sort, you do know still that the energy has a bound from below. Okay, you start at some energy and the energy is decreasing, so at least for some initial time it's greater than or equal to half its initial value or something of this sort. You can make it more specific. That's just for a sense of what's going on. And then it turns out that you can do something of the second form, which can be used at early times, okay? And it's the same structure, okay, but different coefficients and the like, okay? So this is our contribution. And then they were using this from time t equals to 0 because of the autonomy of all the differential inequalities. You can in fact reiterate and use this at arbitrary times again and again, and then you can get sequential values. Okay, and then you want to know the predictions of these different lemmas. So in order to get to the numerical part, which is perhaps more in the context of this seminar, I'll just tell you, you have to run through these different lemmas and see for different energy levels which bounds apply. Okay? So you go through and see who gives the minimum, it's B1 or B2, and then that gives you, if B1 or B2, you get different bounds in the form of EL bigger than B or E bigger than C from the first lemma, and then you go to the second lemma, and you see what powers you're getting in the differential inequality, okay? And you get this sequence of different types of bounds and different types of differential inequalities, and appropriately, therein one gets different upper bounds, okay? With different exponents, okay? Here, this other set of possibilities. If B2 is the minimum, and then you run through all of this, and then the question, okay, but then what can you say out of this? So at all times, you're getting either this bound or that bound, you're always somewhere in the possible tree of bounds and inequalities. So it turns out that no matter where you start in terms of mean concentration, no matter where you start in terms of temperatures, okay, at any given time t, you're getting an upper bound either the first form or the second form, okay? So you get these different upper bounds for appropriate values of the parameters. So because you have to go through and look what depends on what, but you get these upper bounds, okay? Something at all times. At least they look like upper bounds. We'll see that it's a bit not so great as it looks in some sense, but also not so bad. Okay. It requires a bit more thought what these are really giving you. Okay? Okay, so you want to know where you are in terms of this bound or that bound. So it turns out that you can simply divide up energy levels in terms of some E plus, E minus, E11, E12, E21, and E22. Some 6 quantities, energy levels, which depend on what? Which depend on the temperature. Okay? They're functions of the temperature. The bounds and everything written below were given in terms, if you go back, okay?
Boundary conditions don't come into that?
We're neglecting, good question, and I stand corrected, okay? In getting these bounds, we've thrown out the term of the boundary effect because this is sufficiently messy.
Okay, yeah.
But you're right, you would like to go back, okay? Otherwise, okay, it's as if the system were infinite, okay? But one can go back and try. Right, okay? So this is the lower axis goes from 0 to 1, and 0 means that that's the equilibrium concentration is at U plus minus is equal to 0, and the temperature is just at the shallow quench level, okay? And then the 1, that means the equilibrium concentrations U plus minus are at plus minus 1, okay? Which means 1 corresponds to the deep quench limit. What you can then say, this all depends only on temperature. That's the shallow quench, that's the deep quench. And then you get that depending on where your initial energy level is, okay, you start at some, just let go, let's suppose it's just below where it says energy, at some initial time it's there. It's in the up and a functional, it's decreasing, so that at different times you can get these different upper bounds, okay? Some of the upper bounds, the ones with plus, are based on this E bigger than some C. The ones without the plus are based on this LE bigger than some B. Okay, and then you see these are different exponents, and I just wrote proportionality because one has to worry a bit more exactly what is the coefficient of proportionality. So I just mean it's the large time behavior, if the large time behavior is valid when you're going through transitions, is dominated by the power indicated there. Okay? So this looks like that's the whole picture, but then we remember that Cohn and Otto were getting t to the 1/3 and t to the 1/4. So we don't see any t to the 1/4. Oh, we see way over there. Okay? But that small section there, that's for shallow quenches. So why are we getting that over there? And there we're getting this t to the 1/4 for deep quenches. And the whole story is that that's all been crunched into this corner there. Okay, everything t to the 1/4 has been crunched there. Okay. So well, this is just focusing in on this point from before, some crossing in the previous graph at some particular, okay? So you focus in and then you see this different possibility, and you actually get this t to the 2/5, which was never in the original discussion, so it's just a whole new power there, which comes in and then it comes, okay?
So it's a different region. It doesn't contradict the previous one. It's not in conflict with the previous belief. Because
There's
different-
no conflict in the
because
end.
different region of the.
The Cohn-Otto theory was for the deep quench. Okay?
Oh, this is shallow.
And no,
This is very, very close to deep quench, but
Ah.
not quite.
here, this is down to 10 to the minus.
Oh,
Okay, so you have,
so not
the
quite
idea
as deep.
is, you've got to go, you're not at the deep quench, but you've got to go
That's amazing.
real small temperatures, and then you get this coming in. Okay?
But it was surprising.
I was surprised, okay? And also it turns out that really people don't see too much this t to the 1/4. Right.
An explanation.
But in fact, you might, okay, so great.
And
So
this is
Cohn and
numeric-
Otto were dependent and, okay.
But this is numerics, right? It's theory.
No, this is,
Not experiments, not real
this
experiments.
is not real
So
experiments.
could it be confirmed by real experiments? What's the
Okay, so the point is, this is MATLAB.
Yeah.
This is experimental mathematics
Yeah,
in the
experimental
sense
math.
that we've taken all these different E levels and just simply drawn out what the E levels
Yeah, but it's
give you.
supposed to correspond to
This-
real world, right? So
Right. That's what
is
we're
there any way to
also,
compare it to experiment?
yes.
Yeah.
Because these bounds are upper bounds, okay? But they don't say what's the least upper bound.
Oh, so it's not
Okay.
sharp.
It's not, well, it could, we don't know that. I
So it's
mean,
not necessarily sharp.
it's not necessarily sharp, or we don't know where it is sharp, where it isn't. Certain places I know that it isn't sharp.
So it's
okay?
interesting theoretically.
It's at least interesting theoretically because one would be led to believe that t to the 1/4 is a bit rarer than one originally thought. And in fact, in experiments, you don't quite see t to the 1/3, but you see approximately t to the 1/3 with some deviation at mean concentrations off 50, quite far off 50/50. Okay, but t to the 1/4 isn't something quite seen. So this was some initial explanation of perhaps something reflecting. It could be not contradictory to experiment and not contradictory to Cohn and Auto, but it's still not saying it precisely what's happening.